today probably will be rather modest because at the end I will explain how to complete some integrals. But on the other hand, so I follow here my colleague and friend of one day, Vladimir Fatiev, who said once that everything will be gone except for integrals. So exactly compute of integrals will stay. So I'm not sure that so anyway, so I will not go into much details in the introduction, so but I have to say a few words, and probably Herman after will say more about all this stuff. But so the point is that for many years we are working on this basis. So the goal is that if you want to compute, for example, a one-point function of an operator, then this is done by this fermionic basis. So I'm talking about similar. But also there are two things. So first of all, the one-point function in the fermionic basis are easy to compute with some special functions which I don't explain. So probably Herman will. But so the point is also there is a problem also of normalization, because you want to know which exactly operator do you construct, and then you have to have a dictionary between this fermionic basis and the operators which are counted by ultraviolet conformal field theory. And then since there are some arbitrary constants in this problem, so we believe that there is one-to-one correspondence between the ultraviolet conformal field theory description and what operators after the information, just because for the simple reason because all the finite counter terms can be discovered because of for dimension reasons. So, and today I will be talking only about CFT, so fermionic basis in CFT. And so this we were doing with mu and G long ago, but the problem is that our consideration first of all was and then was very complicated. And also Herman Boss computed one contribution, so we could go up to certain level, but it was very hard to go any further. And so then with Stefano Negro, we realized that actually we can use the framework of reflection relations which were discovered by Fatiev, Lukyanov, Zamolodchikov, two Zamolodchikov. Yes, so I will explain what it means. So that, roughly speaking, this reflection relation solves this solves the reflection relations. So to fix the notation, so central charge, so I consider Virasova, and central charge is like that. So does it look?
The laser pointer doesn't work.
So do I have something?
Your hands.
And so scaling, so I consider primary field. So arbitrary scaling dimension. So say you are doing the generalized minimal model, something like that. So this is the scaling dimension. And so we, for the moment, to begin with, we will work with space which is a quotient of Werner model by function of local integrals of model. This is some commutative subalgebra and nodes also. So, and so then this quotient space, there is no, of course, canonical way to define the quotient space, but I will define it by action of Virasoro generators with even indices. So there will be this number of this is the number of partitions, yes, of n over 2. Level for me will be even. So, and then we have also the same thing. The same model can be described by the Heisenberg generators. So I have Heisenberg generators here, and so I define some basis. The only requirement is that I take even. So after a to minus a basis for Heisenberg, but so then it is not uniquely defined. But I take any one. So any one which I like. So and then the reflection relations. So we have these Virasoro vectors. This is V is for Virasoro, and we have Heisenberg, and we have matrix which again. So I will not. So when I'm writing this sign, so it means that I'm working modular universal motion. So I'm working modular local universal motion, so I can rewrite the Virasoro generators in terms of these Heisenberg generators. And so the important thing is that we prepare our model for deformation to get Sine-Gordon model. And the Sine-Gordon model, of course, there is C-symmetry, yes, pi to minus phi. Pi to minus phi symmetry, right? And so, but in this Virasoro, what is it? No.
It's a screen.
Do it again and.
That has plastic at the end.
So, and so the idea is that we want somehow to be invariant under two reflections. So alpha 2 minus alpha, which is inherited from the CFT, and this alpha 2 minus alpha, which is for further application to the Sine-Gordon. So in some sense, so this CFT invariance is rather poor. So this is a kind of wild group of SL2, so not very. But this is already a fine. So, and then, as I said, so the reflection relation. So I will. Let me see. What is that? So I will be talking about some other basis, so which is created by some fermions, so with odd indices, and so this basis, so this reflection relations will be kind of automatically restored. So this basis, this harmonic basis, is related to the original one as follows. So first of all, it's convenient to there are some special functions, transcendental functions coefficients inside, so it's convenient to take them out. So this is some gamma function. And so then if you take it out, so then the relation between this fermionic basis and the Virasoro basis must be like that. So there are some polynomial in Virasoro generators which is called even. There is one odd one, and so then the point is that so here there is some funny constant delta alpha. We change signs after under alpha to 2 minus alpha, and so but on the other hand, so the coefficients of these polynomials, they are functions of delta of the scaling dimensional order, so they are automatically invariant after alpha to 2 minus alpha. So this is the definition. So this is my kind of my Virasoro model description. So I want everything to be invariant under this reflection alpha to 2 minus alpha. And only this guy is odd, so it changes sign.
Fyodor, in general, you don't know P even, P odd, right? Do you know P even and P odd in general, or just?
Yes, no, I don't know. In general, no. But so I will explain procedure how to get them. Mm-hmm. Yes. So I did not say that this is when I write this index, multi-index here, so it's the product of fermions, and so this is also the product of fermions, and later we will use also this products of local integrals of motion. So now the reflection relations. Eventually you reduce them to some kind of Riemann-Hilbert problem. So finally, so we are looking for some vectors. The number of vectors is the same as the dimension of our space, as the number of our fermions or whatever. And so of this quotient Virasoro space, and that satisfies this kind of relations where, so you see, I shifted alpha by 2, and I got some rather complicated multiplier here. S is constructed out of this matrix U, which I had before, which relates the Virasoro basis to Heisenberg basis. So, and I don't know. So for people who remember still the quantum mechanics, so this is like S matrix. It looks like S matrix is a product of two wave operators. Yes. S is equal to U, or U minus. So the examples of this U's are given here. So it is simple to solve it for level 2 Virasoro, because this is just a constant. So you just factorize. It's one dimension. Just factorize this, and this was done by Lukyanov, Fatiev, and Zimolov. So then for already this is rather ugly, and then it's getting more and more complicated. Nevertheless, it can be solved. So let me explain how the solution in this quotient space looks like. So first of all, we have this operator which U once again, which
short question. For level 2, it's solved in terms of Barnes function.
Gamma functions, yes.
It's Barnes function.
With gamma functions.
It's many gamma functions called Barnes function.
Gamma functions isn't so
okay, my question is higher levels.
Let me see. You have such an equation, and the multiplier here is a rational function. So you solve this equation with the finite product of gamma functions, right?
For any level.
For level 2.
For level 2, but for higher levels.
This is what I'm going to explain. So, for higher levels, as I said before, so it looks like the solution looks like this. Yes, so you have the transcendental functions are only gamma functions here, and so there will be products of them. Yes, because so I have many fermions. There will be products of these guys, and then there will be some polynomials in delta. So products of gamma functions, finest products of gamma functions, but so can be long, and some polynomials. So, let's see. So, if we compute the determinant of this matrix U, which relates Heisenberg and Virasoro, then the determinant will have some multiplier, which I don't explain. So this multiplier is just a product of so you see, there will be some contributions from singular vectors. Yes, so it will be just product of monomials corresponding to contributions of singular vectors. Of course, of all null vectors. Of course, so with multiplicities. But this I don't care too much. So then there will be something which I called Virasoro determinant, something which I called Heisenberg determinant. And so then this P even and P odd in Virasoro must be supposed to be as follows. So there is some the denominator here, and then some polynomials in just linear combinations of these Virasoro vectors, and so coefficients are polynomials in delta and C only. So this is a requirement that depends only kind of only on Virasoro data. Yes, and so these guys, these polynomials are of degree D in delta, and this degree, for the moment, I'm not saying what is this degree. This has to be defined. But then I go to the Heisenberg side, and what I said before can be reformulated as follows: that the same thing allows another representation from the Heisenberg side, that I have also Q even and Q odd, which depends now on the Heisenberg scaling dimension, which is just alpha squared. Yes, and so this G alpha is just antisymmetric with alpha to minus alpha. And so these coefficients of these two polynomials, they depend only on alpha squared. And so this is some product of monomials which comes from this product of gamma functions which I had before. So, and then I start to solve this thing. So I introduce some even odd polynomials like this. And so I probably, it is too much of details. And so then eventually, so everything reduces to the following two requirements. So the fact that starting from Virasoro, we get symmetric under alpha to minus alpha Heisenberg operators is equivalent to these two requirements. That this ugly thing is even in alpha, and this is less ugly. So, and if you count the number of equations which you get this way, so the number of unknowns is like that, but the number of equations is much, much higher. And so the fact that these equations allow solutions is a miracle which is produced by our fermionic basis. And so because so even if you have many equations, so it does not mean, first of all, it is not obvious that they have solutions, but even if they do, so it does mean that they have all the solutions. Yes? So, but I have no proof that this is the case, but I found solutions up to level 12. I was not waiting to do it up to level 12, and so it works. Yes. So just for curiosity, so this is a solution which is easy to find in this procedure, but which Hermann both found from other perspective long ago with rather complicated procedure. So it is in fermionic basis it is beta 1 star, beta 3 star, gamma 1 star, gamma 3 star, gamma 1 star, and it is given by this. It is on level 4, right? So it is L minus on level 8, sorry. It is L minus 2 to degree 4. Then this guy, so partially this is how it looks like, yes? If you are curious. So, but this guy is symmetric under this change 1, 3 to 3, 1. There is no odd part. So you can enjoy this thing. So I'm not sure it will remain.
I remember only denominator, delta plus 11.
Yeah, delta plus 11. So yeah, for some time the delta plus 11 is sorry about this. Delta plus 11, yes. So it is very, very misleading thing, because for some time I believe that the denominators factorize in delta, but this is not the case. The denominator are very complicated. So starting from level 10, they become complicated. And so that's why I don't write. I don't bother with C. So now let's see. This is very nice. And what is it good for this fermionic base? As I said, it is good, for example, if you compute the one-point function for sinusoidal model, if you compute the one-point function on a cylinder, yes? And so the boundary, so for the ground state, so in Matsubara direction, so the boundaries are the same to the left and to the right, yes? So then, of course, this quotient space which I described is quite all right for you, because the local integrals of motion, they do not contribute, because so it's like so they you have, in a sense, if you wish, you have an adjoint action, and then you move these guys to the left and to the right, so they vanish. So that's why only this quotient space is sufficient. But now suppose you want to do something more sophisticated, and you want, for example, to compute the one-point function for with different twists to the left and to the right. So which means that you will have all these different states to the left and to the right. So you will have then you cannot anymore throw away the action of local integrals of motion, because they will contribute. And so you have to solve this reflection relations in entire Virasoro space, not only in the quotient space, but action by left action of a lot of integrals of motion. And so, but this is the first, you think that now you have to start to redo everything from the very beginning, but fortunately not, because so, let's see why I am here. But fortunately not, because so if you already solve in the quotient space, then solution then adding the action of local integral motion leads just to linear difference equations. So let me explain this. So I had this, how it's called, congruency, yes? So I have this kind of relation in the quotient space, yes? So now I want to generalize it to the entire space, and I start, of course, so as you can imagine, so when I want to do something, I start from the opposite side. Yes? So I start from this right-hand side here, and this right-hand side here, I just rewrite it. I forget about my. So this is a well-defined. This is a well-defined expression in the Heisenberg model. Yes, so I forget about this portion, and I just rewrite this in terms of this guys. So here probably this is not the best idea to use this, but it's all right. Yes. So I want to rewrite it. So the first term is what I had before, but then I add some descendants created by local integrals of motion. So here it's, this IK is descendants created by local integrals of motion. IK is, I said, this is a product of integrals of motion. Yeah, and then in order, I don't want to spoil my. I don't want to spoil my relation, my symmetry alpha to minus alpha, which I had before. Yes, so that's why this coefficient b, which I add, must be symmetric under alpha to minus alpha. Yeah, and then when I require, so let me see. So this coefficient c is something which I calculated. I calculate. I don't know. So this is, they are ugly, but they can be calculated. And now I add thing like that in order to satisfy both reflections. So, and I want to spoil. I don't want to spoil the first reflection, alpha to minus alpha, and that's why this must satisfy this symmetry. But then I require this symmetry alpha to 2 minus alpha, and it eventually gives me the following equation. So these guys are known, and this is so this is a linear difference equation for this coefficient b. Yes. So so it's quite remarkable that I have a linear equation. So the only thing is that I have to say, so when I have a linear difference equation, then I have to say something about boundary conditions, so I don't know, singularities and so on. So for the singularities, it is, the idea is simple. You don't want to, you require that in the strip alpha from 0 to alpha to 2, there are no singularities. This is quite natural. But on the other hand, I also require that when alpha goes to I infinity, plus minus I infinity, this goes to constant, so which is probably not so natural, and I don't have a good explanation to that, but to this, but so somehow it works. So then I skip. So let's consider an example of level 2, which was level 2 was trivial for this portion space case, because so the fermionic basis was found just by this gamma function, yes, so because the matrix was 1 by 1. But now, so there is some addition, and with the only thing you may have on level 2 is L minus 1 squared. L minus 1 is I1 for me, yes. And so then when I solve my difference equation, the answer is as follows. So it is, so from now on we will need this Лукьянов-Замолодчиков, Богданов-Лукьянов-Замолодчиков constants, yes, all the time. So which this is a normalization of local form. So this is, so this part is something simple. So then there is a constant which I will explain, and so then I solve my difference equation. So this is a solution to my difference equation. These are my requirements that it is regular from 0 to 2. Yes, and so then, okay, I said it is regular for alpha from 0 to 2, and it goes to constant when alpha goes to plus minus I infinity. But this is exactly the problem, that constant is, this constant is not defined. And so now I will explain how I define this constant, because so this is this constant which I put by hands, and I will explain why I did that. The explanation goes through the singular vectors. So I have or null vectors in general. So I have new description of the conformal field theory, yes? And so, but in the conformal field theory, in terms of these fermions, but in the conformal field theory, so there are null vectors. So you have singular vectors and then their descendants. And so you want to describe them in this new basis. And this problem was up to some generalization solved long ago in our papers with Olivier Babylon and Denis Bernard. So it looks as follows. So it may look complicated, but actually it is not. So you have some functions, so some simple functions, which everything here depends only on the polynomials, only on periodical two periodical functions on alpha. Yes, sir. And so there are these generating functions for the integrals of motion, and so there are two operators. One is odd in fermions, which is like that, and another is even in fermions, and it is like that. But the coefficients are either integrals of motion or some very simple periodic functions like this cotangent. So nothing complicated. So, and then the general statement is that the null vectors, so for these phi fields, phi mn, okay, phi mn, so I had alpha before, but you can easily relate alpha to mn then, of course. But so there are two things for even n. There are only this kind of, so you take space which with charge minus n, so more gamma stars than beta stars. And then you act by this operator, and so this is one null vector, and there is another null vector, and all this story altogether goes under the name under the name of quantum Riemann-Bellini identity, but this I will not explain at all. So let's see. Let's consider an example. So a simple example is if you take the this gamma 3, gamma 1, and act by C1, then you obtain this guy. So this is my procedure, that if you have to have here charge 2, for example, charge -2 to get charge 0 here. So, and this is like that, so this must be a null vector. Null vector from Virasoro side is of course like that, so you can easily compute, yes? So, and for my fermionic basis, so it means that I have such an identity in order that this is satisfied. But here, of course, everybody would say that I am cheating because so I just put this constant by hand, and now I cancelled it, so I get 0. So I can constant. It's not a big deal, so not very impressive. But now there is an interesting thing that you have one more singular vector, which is for which you need only this fermion beta 1 star, gamma 1 star, namely the first descendant of the integral of motion. And this is more interesting. So this guy looks like that, yes, so you have to take 3 of this and act by this q, and you obtain this left-hand side, which must be equal to that. And this is already interesting, because so the coefficient of this, the main coefficient, this I1 L minus 2, is automatically correct. I just choose this by normalization. The first non-trivial identity here is that C3, this Lukyanov-Zamolodchikov constant number 3, is like that, according to this relation. This is true. With gamma functions, so you check that this is true. But now there is one more guy remaining. So you have to check that I1 cube is correct. And for I1 cube, we got already an integral relation. So this is where we all recall Fateev. Yes. So I mean, the citation I gave. Yes. So if you compute everything carefully, so then the identity you are supposed to have looks like that. And of course, nowadays modern people will put this thing on the computer and we check and this is correct. But so then we want to understand how it works. So. And so this is the first thing, and so this I will explain this integral. But so the point is that there are infinitely many relations for integrals of this kind, and not only so some integrals are single, some integrals are multiple. So they satisfy. So actually, I cannot say that I even numerically I went too far. I checked up to level 6, not more. But so every time it works nicely. But so there is a great number of identities of this kind, and this is quite amazing to my mind. Let's try to prove this identity. So let's denote this product of gamma functions by G. So this is a thing which I had in here, but I want, because I will continue analytically, I don't want I don't like the absolute values. So introduce this function, and now consider such a function f, and so then it's easy to see that this f is a difference, that this g is a difference by t by g is difference by f plus of t plus 2I minus f of t. And so then this means this allows to compute an integral along the real line of this tg, because this is just different. So you make this integral to difference of two integrals, and it is sitting on at only one pole inside. So now, if I denote the, I don't know, so yes, so this I of p is the integral of in my lemma. Yes, and the integrand is like that. And now I compute I of p minus 2, and this is like that. Yes, so just once again, so I use some simple analytical continuation, and so at some point I come to the following relation, that this I of p multiplied by p minus 2 minus I of p minus 2 multiplied by p squared minus 1 is equal to this expression, so essentially expressed in terms of gamma functions. And so now I am happy, almost, because then the function like that is periodic. And so the only thing I have to do is to fix. So it is periodic, and it's easy to see that it is also decaying. So I have to fix its poles, and yes, that's essentially that's it. So periodic, and the only pole, it's easy to see the only pole is there is only one pole, and so then it is. This function is proportional to 1 over ch hyperbolic, and the coefficient, which is pi over 12, is easy to find. So by taking some particular value. So, and so, I don't know, so probably this kind of rather barbaric way to proceed, so probably somebody has better idea, but I must say that long ago with Miva we were exercising, because, so, let me see, because, let's see, so, yeah, so it's easy to see that if we know the solution in the quotient space, then it's easy to see that, dealing with the space, which is the next one, linear in the integrals of motion, descendants of the quotient space. So that this is also doable. And so this is reflected by this identity which I wrote here, so the first non-trivial identity. But we can exercise with this linear in integrals of motion, guys, and we did it with Miva long ago, and we got a huge amount of data. And at this point, we thought that it is a shame that we cannot interpolate this data, and we cannot write an explicit answer for. At that time, we didn't know about the Hessian relation, so it was we were practicing by different way. But anyway, so we were thinking that it must be explicable, impressible in terms of some simple functions. So, and we tried, and we could, we failed, and we were very afraid. So, but we are lost. But so then the point is that actually the thing is more complicated, and so then that there are some integrals, and now if you, for example, if you want to have, I don't know what, say, 1-point function or 4-factor, whatever, not of some operator, but of given operator, for example, of L minus 2, without any additions. So then, or of L minus 4, or of L minus 2 squared, or I don't know what. So then, the point is that the answer, if you want to have a particular operator, the answer will be rather complicated, and it will include this kind of integrals. Even in the simplest case, if you want to know how the given 4-factor or 1-point function for different boundary conditions looks like, so you will have this integrals there. And further you go, more complicated stuff you will have. So in some sense, it's long, it solves the problem, but I don't know why. Why? Okay, so thank you.
Thank you very much, Fedor. Other questions?
Fedor, is there any compact form of level 3 coefficients?
Level 3.
Compact means fit the slide.
Level 3. So I don't have it here, but of course, yeah, this is level 3. But level 3, what is level 3? Level 3 is what I was talking about. Yes, level 3 is descendant of level 2, right? So, but this is what was written.
Yeah, but do you have it compactly written so to observe it?
You see, so,
Or maybe you can repeat it.
On the level 2, I had this formula, yes? So, which includes the descendants of local integrals of motion here. And so I plug it here, so I don't know how, so on one slide, so this is on one slide, I suppose.
I have to comment on the quote you gave. I mean, about what will be kept and what will be forgotten. Still another positive, I would say. I remember a theoretical physicist working more down to earth and materials, etc. He was frustrated when once, and he said, or he predicted about his own work, everything will be forgotten except one trivial mean field calculation. So it's better to have interesting integrals.
Okay. That also makes sense.
So, we still have 5 minutes time. Maybe wait for a few seconds. Okay, so maybe thank Fedor once again.